Good morning, everyone, and welcome to your first day of C19, Unit C19. Hopefully you get it. We are going to get started with our improper integrals, and we're moving on to our last unit of calculus. We are moving ahead as if the AP is scheduled on our date. We're going to see what Mrs. Surface can do with about getting us a 2-week extension, but we are going to keep on learning. So make sure you reach out if you've got questions. Talk to each other like you guys always have been doing, but try to get as much out of this as you can. So, yeah, do your best, guys. I know it's kind of hard and strange and bizarro, but that's what we were dealing with. So I've linked all the notes on, you should have those pulled up, printed out, or just taking those on a separate sheet of paper. You are going to have to do this in Edpuzzle, so please don't switch over just yet to YouTube. We are going to have some questions to do throughout it, but let's get started. So what I first want you to do is pause the video and do exactly what it says. Use your calculator, figure out these values, and then we're going to come back and talk about these two words, converge and diverge. All right, here are the numbers that you should have gotten. And as you look at these as we're changing the upper bound, you can see that the sum of the integral keeps getting larger. So when we talk about the words converge or diverge, converge is going to mean to go to a specific number. Diverge, much like the book Divergent, means they're going off on their own. It's kind of like a runaway train. You never get to exact value. It just keeps on going in some direction. So if we're looking at this sum, it keeps on going. And it keeps on going to infinity. So we're going to say that this integral diverges. And it diverges to infinity. It keeps getting larger and larger. If it would converge, that means if it comes together, that it's going to stop and it's going to go to a particular number. And in pre-calc, we've looked at series that converge and diverge by looking at infinite geometric series, and we're going to talk a lot more about that in this, which is why it's called sequences and series. So let's head on over to the next slide. Pause this and answer questions 4 and 5. So what you get here is you notice that as you change the upper bound from 100 to 1,000, you're still getting the same sum, 0.386 or 0.3678, blah, 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 blah. But if we keep changing that upper bound and if we make it infinity, it's probably not going to change that because we've already noticed that if we're changing our upper bound from 100 to 1,000, it didn't change. So if we make it even larger and go to infinity, it's not going to change. So we say that this converges. And if you don't know this, which I don't expect you to, this converges to a special number, which is e to the negative 1, or 1 over e. And when we take a look at those sketches of each of those, it kind of shows you what you're working with here. If you graph these with your graphing calculator, you're going to notice that if you look at f of x, we've got 1 over x, so at 1 we're at 1, at 2, we're at a half. If we're at a half, we're at 2. So it's going to slowly get closer and closer to the x-axis, but it's going to take a while. Conversely, if we take a look at f of x equals e to the negative x, if we plug in 0, we're going to get 1. We've got 1 over e, and then we get, they're a lot faster with this graph. And what you notice is that it pinches it off a little bit different. So if you actually change your windows to go from 0 to 5 and negative 1 to 2, and then go from 100 to 500, and changing this to a really small y value, you can really see what's going on there. So let's take a look at this. These are improper integrals. They are improper because the upper or lower boundary of the integral is an infinity or negative infinity. When you're taking an improper integral, we need to replace the infinity with a variable, and we're going to take a look at what happens to the integral when we take the limit as b goes to that infinity, whether it's positive or negative. So let's take a look at a couple examples. If we have the integral from 1 to infinity of 1 over x dx, we are going to need to replace the upper bound with our variable. Traditionally, it's b. So we're going to take the limit as b goes to infinity, and now our integral becomes from 1 to b of 1 over x dx. And that integral of 1 over x dx should be familiar. That becomes the natural log of the absolute value of x. And we still have the limit, and this still was a definite integral in the sense that we are evaluating this from 1 to b. So now we're taking a look at the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. And we can even simplify that further because we know our natural log properties. We've got the limit as b goes to infinity of the natural log of b over 1. And since b is going to positive infinity, we don't need to worry about our absolute value here. We're only looking at those positive numbers. We get b over 1, which is just b. So if we look at what's happening to the picture of the natural log function, here's the graph of my natural log, and as x goes out to infinity, or as b goes out to infinity, that y value is still ever increasing. And since this is going to keep going to infinity, we say this diverges. It doesn't really have a number that it goes to. It's just going to keep getting larger and larger and larger. And we leave it at that. So let's take a look at another one. The integral from 1 to infinity of e to the negative x dx. So like the other one, we're going to make this a limit as b goes to infinity of 1 to b of e to the negative x dx. We're going to take the antiderivative of e to the negative x, which of course would be the opposite of e to the negative x, chain rule, evaluated from 1 to b. We're going to put our definite integral boundaries in. The opposite of e to the negative b minus the opposite of e to the negative 1. Now let's rewrite those and see what that actually looks like. The limit as b goes to infinity of the opposite of 1 over e to the b plus 1 over e to the first. So as b goes to positive infinity, we're taking e to that positive infinity power, and this is going to get an infinitely large denominator, which means this term is going to 0. As we go to infinity, this term is unchanged. So our answer is 1 over e, which means this converges to 1 over e. All right. Why don't you give this a shot and try and see what you get for this? So the first thing you should have done is change it to a limit problem. Sometimes people like to use the letter a as they're going to negative infinity to differentiate between a lower bound and an upper bound, but it doesn't matter. So I've got the limit as b goes to negative infinity from b to 0 of e to the 1/4 of x dx. The integral of an e to the x power is e to the x unless there's a chain rule component. So if we're dividing by that power, dividing by 4, it becomes e4 times e to the x divided by 4. And we're evaluating that from b to 0. So when we plug those in, we've got e4 times e to the 0 minus 4 times e to the b over 4. Oops, forgot the negative here. So when we're taking a look at the limit as b goes to negative infinity, if we've got 4 times e to the 0th, e to the 0th is 1. Don't have to worry about that. And when we're taking e to a really large negative number, we need to imagine what e looks like. E is an exponential function that as I go to the negatives, I get infinitely closer to 0. So this term will disappear and become 0. So all we're left with is 4. So this converges to 4. You can also see this when we're talking about revolution. If we've got e to the negative x, that's just the graph we just drew reflected across the y-axis. There's e to the negative x. We're going to take it bounded in the first region about the x-axis. So we want this space right here. We're revolving it around the x-axis. So it's kind of looking like the end of a golf tee, but narrowing out and tapering further at the end than a typical golf tee would. But if we're going to take the volume of this figure, we're going to take our pi, because there's a no inside radius, so it's a disk. We're going from 0 to infinity of our radius squared dx. So we've got pi. I'm going to change this to a limit. B goes to infinity of the integral from 0 to b of e to the negative 2x, because when it's a power to a power, we multiply. And we're going to integrate that. So pi, we've got the limit, b goes to infinity of negative 1/2 e to the negative 2x, and we're evaluating this from 0 to b. Pi is still on the outside as the limit goes to infinity of negative 1/2 e to the negative 2b minus a negative 1/2 e to the 0th power. And we can write e to the negative 2b, as we're thinking about it, as negative 1 over 2 e to the 2b. So what's going to happen to that as we go to infinity? That's going to go to 0. This goes to 1, and we've just got plus a positive 1/2. So we've got pi times a half, which is just pi halves. So that's the volume of our shape if we are revolving this region about the x-axis. Even though we're going to infinity, we're not going to go to a number that ends. It's still going to get us a finite number.